Welcome to this video on vertical kinematics, where we explore a ball being dropped to the floor. A ball is dropped from a height of 1.5 meters above the ground. In part A, we'll find how many seconds it takes the ball to hit the ground. In part B, what the ball's velocity is the moment it hits the ground. And in part C, how far from the ground the ball is after falling 0.4 seconds. We start part A, how many seconds does the ball take to hit the ground, with a diagram on the right, and listing our variables down the left-hand side. So let's add what we know from the question to our diagram. So we know the ball drops a vertical displacement equal to 1.50 meters. Now, because it's dropping, it's negative. It's going down 1.50 meters. Direction is very important in kinematics if you want your answer to come out with the proper direction as well. In this question, we also have acceleration due to gravity, also goes downwards, equal to negative 9.81 meters per second squared. And finally, we know the initial velocity of our ball. The ball is dropped, so it has an initial velocity equal to 0 meters per second. The ball is not thrown downwards, it's just released or dropped. Now we're ready to add our variables down the left-hand side. So we have a velocity initial equal to 0 meters per second because the ball is dropped. It's not thrown downwards, so it has no initial velocity. We have a displacement equal to negative 1.50 meters. We've defined down as negative. So our displacement is negative. The ball drops downwards. We have an acceleration due to gravity. We know this is equal to negative 9.81 meters per second squared. Again, we've defined down as negative and gravity is going down. In this question, we're searching for our time. So our time is what we're looking for, and we might as well add the velocity final in here as well because that's what we're going to be looking for in part B. We're now ready to pick our kinematic equation. In part A, we're looking for a kinematic equation with VI, dA, and T. We don't have, and we're not looking for VF, so we can just cross out all the equations that have VF in them. So this leaves us with this kinematic equation right here. Displacement is equal to velocity initial multiplied by time plus 1/2 the acceleration and the time squared. And now we're ready for some numbers. Our d is equal to negative 1.50 meters. This is equal to our vi, which is 0 meters per second multiplied by t, plus 1/2 multiplied by our acceleration, which is negative 9.81 meters per second squared, multiplied again by t squared. This term here is 0. So we rewrite this as negative 1.50 meters is equal to 1/2 multiplied by negative 9.81 is equal to negative 4.905 meters per second squared multiplied by t squared. Next, we want to get our t squared here all alone. Negative 4.905 is multiplying t squared, so the opposite of multiplying is dividing. We divide both sides by negative 4.905 meters per second squared. And on this side, the two terms just cancel out, so we're left with our t squared term. And on this side, negative 1.5 divided by negative 4.905 gives us 0.3051 seconds squared. We'll keep a few extra terms so we don't end up with any rounding errors. And finally, to get our value of t here, we just take the square root of both sides. So the square root and the squared on this side disappear, leaving us with just t. And this is equal to 0.553 seconds. Now, technically, because we're taking the square root, this answer could be positive or negative, but it doesn't really make sense to have a negative time, so we know that our answer is going to be positive. Let's add this time to our list of variables before moving on, so 0.553 seconds. In part B, we're asked, what is the ball's velocity at the moment it hits the ground? Well, since this is the same setup as part A, we can use the same diagram, and we can use the same variables down the left-hand side. So we're immediately ready to pick our kinematic equation. We can technically use any one of the 4 kinematic equations because we have 4 of the variables and only one unknown. But let's err on the side of caution. Remember, we calculated the time in part A. And if we got this time wrong and we use the time in our next calculation, that means we're also going to get the next answer wrong. So let's use an equation that doesn't have time in it when we're finding VF. So our first one here has time, this one has time. Here's our equation without time, and just to double check, this one also has time. So we're going to use this equation to solve for the ball's velocity at the moment it hits the ground without using time. Vf squared is equal to Vi squared plus 2 times the acceleration multiplied by the displacement. Now we're ready for our numbers. So Vf is what we're looking for. So Vf squared is equal to our Vi squared. Well, that's 0 meters per second squared plus 2 multiplied by gravity, which is negative 9.81 meters per second squared, multiplied by our displacement, which is negative 1.50 meters. So our 0 squared, well, this term is just 0. It doesn't exist. So Vf squared is equal to 2 multiplied by negative 9.81 multiplied by negative 1.50 equals 29.43 meters squared per second squared, because our meters here multiply, making meters squared, and our seconds squared just stay here. And now, since our velocity final is squared, we have to take the square root of both sides. So our square root and our squared here disappear, leaving us with what we're looking for, our velocity final. And this is equal to the square root of 29.43, which is equal to positive or negative 5.42 meters per second. Why is this positive or negative? Well, remember, when we're taking the square root, you can get both a positive and a negative answer. Another way to think about this is negative 5.42 multiplied by negative 5.42 is equal to 29.43. Similarly, 5.42 times 5.42 is also equal to 29.43. So when we take the square root of this, we could end up with either solution. Now, in physics, we have to decide which answer is correct. We define downwards as negative. When our ball hits the ground, it's going downwards. So we know that our final answer for the VF is negative 5.42 meters per second. We can add this answer to the side before moving on to part C. So our velocity final when our ball hits the ground is negative 5.42 meters per second. In part C, we're asked how far from the ground is the ball after falling 0.4 seconds. So some of our variables and some of the aspects of our diagram no longer apply. Let's start with our variables. So our VI is still 0 meters per second. The ball is released. It's not thrown downwards. We found in part A that it takes 0.553 seconds for the ball to reach the ground. So we know the ball's not going to reach the ground in 0.4 seconds. Gravity is still gravity. It's equal to negative 9.81 meters per second squared. And we're no longer reaching the ground. We're seeing how far the ball goes in 0.400 seconds. Our velocity final, this is also from hitting the ground. So again, this value is no longer valid for part C. We do need to be a little bit careful when we're solving for this problem to make sure we don't solve for the wrong thing. So we know the ball comes up short of the ground and we're asked for that value. How much does it come up short of the ground? What we're actually going to find in this question is how far the ball drops here. Let's call it D. D for ball drop is equal to in a time of 0.400 seconds. So we'll indirectly find this D here afterwards by subtracting what we find here for the drop from the overall distance. We update our variables accordingly to match our diagram. So let's call this dd for d drop, and we're ready to pick our kinematic equation. We want a kinematic equation that has vi, our displacement, d, the acceleration, and the time. We don't have, and we're not looking for vf, so we can just cross out all the equations that have vf in them. This leaves us with the kinematic equation we want to use to solve this problem. So if we write this up here, the displacement is equal to vi multiplied by time plus 1/2 multiplied by the acceleration multiplied by the time squared. We're now ready for some numbers. So our displacement d is what we're looking for. We called it dd to find the displacement of the drop. It's equal to our vi, which is equal to 0 meters per second, multiplied by our time, which is 0.400 seconds. This is all added to 1/2 multiplied by the acceleration of gravity, which is negative 9.81 meters per second squared, multiplied by time squared, 0.400 seconds squared. So our term here is multiplied by 0, so it just goes to 0. That leaves us with our d. d is equal to 1/2 times negative 9.81 times 0.400 squared. And this gives us a value of 0.7848 meters. So our seconds squared cancel with our seconds squared, and it leaves us with meters. We're now one small calculation away from finishing this problem. Remember, we're looking for this value. The question C asks how far from the ground is the ball after 0.4 seconds. What we found was this value here, which is how far the ball dropped. We know the total drop is 1.50 meters, so we could just subtract what we found from the 1.50 to find out how far the ball is from the ground. So the distance to the ground minus the distance of the drop is equal to the distance from the ground to the ball. We add in our numbers. The distance to the ground is 1.50 meters. The distance of the drop we just found up here is 0.7848 meters, which gives us a distance to the ground, if we subtract these two numbers, of 0.7152 meters. So our final answer, distance, is equal to 0.715 meters from the ground. Thank you for watching this video on kinematics, where we explored a ball being dropped to the ground.